Hey, Rex.
Hello.
Morning, Nathan. Okay, it's 10 o'clock. We'll go ahead and get started. We're going to focus today on questions 6 and 7, or questions related to 6 and 7 that are on the paper test. The first one here talks about the equilibrium concentrations of ionic species resulting from dissolving a salt. So if we're looking at a situation over here, let's say we've got use this example in the PowerPoint, and it's MgOH2, and that's a fairly insoluble salt. So what will happen is that you'll see particles of the salt on the bottom of the beaker, but then some of these particles will split apart, but they'll split apart pretty predictably. So each one that does split apart will split apart into one Mg2 plus and then two OH minuses. We can come up with that's a solid there, we can come up with a KSP expression. If you need more on this, you should watch the video. It looks like that. And the squared, of course, comes from the fact we've got two OH minuses there. It's almost like the MgOH2 solid doesn't really matter because it doesn't have a concentration associated with it because it's a solid. So the only thing that really matters is the aqueous ions that we get from the solid dissolving in the solution. We are given in this kind of problem a KSP value, which allows us to figure out what the concentration of these ions is going to be. So on this fall 2018 test, you can see that that's what we've done. When we initially put this into the solution, there should be a solid here, by the way. There's certainly no concentration of the solid, but there's also no concentration of the ions either. But after a while, we let it sit, and some of these will end up dissociating, and we end up getting equal numbers of Ag plus and acetate ions in this instance. So the KSP value here can be then calculated because we can solve for this Z value here, and then we can plug that back into the equation. So let me get another example here, and something a little bit more, something that shows a different Z value than what we have here. I'll try this one here. Just click on it. All right, so this is a better example that shows values for Z that have coefficients different than 1. So you can see how this works out. We've got 0 and 0 initially, then at equilibrium, we'll have 2Z and 3Z. Now the Z here, it just means a certain amount, and the ratio will be 2 moles of Fe3 plus for every 3 moles of chromate that we get, which makes sense because that's what the iron chromate looks like. If I drew a picture of it, it would look like this. Be 2 Fe's, and then chromate would be 3 of these. Now that has a -2 charge, which means the ions would have to have a +3 charge. So you can see we get 2 Fe3 pluses for every 3 chromates, or CrO4 2 minuses that are there. You can see how the math goes then. We are given the KSP value here, and then we can plug in these values into the KSP expression, which I wish the student had written down, but I'll go ahead and write it here. So KSP is equal to Fe3 plus squared and CrO4 2 minus cubed. And you can see that then we're just plugging in the values and then solving for Z. What can be challenging here is just how you enter this into the calculator and how you make these calculations. I meant to ask, can everybody hear me?
Yes.
Yep, absolutely.
Thank you. All right, so I'm hoping you can see that when you're doing the square and the cube, you're squaring and cubing everything that's in those parentheses. So 2 squared is 4, and 3 cubed is 27. 4 times 27 is 108, and that's where 108 comes from. In order to solve for z at this point, what we need to do is take the 5th root. And that can be done by putting it into the calculator and then putting it to the power of 1 over 5. That's how you can take a root of something, is by 1 over that value. And that gives the z value. And then that can be plugged back in here to calculate whatever z happens to be. Does anybody have any questions about number 6? Does anybody have any questions about the extra credit quiz that goes along with this one?
So for the extra credit quiz, it asks to find like the POH.
Right.
Given the KSP. So do we go through the whole process and then we go through the process of finding like the POH by doing POH equals negative log of OH?
Right. That's right. So I'll do an example of that since you asked. Let's see, that's be under here we go, solubility in KSP. I'll do an example from the practice quiz here. To move this somehow. Okay, so let's say we've got this one here. This is the AOH5. Now, the way I'd handle that is I'd have my AOH5 solid. And I'd have to know how that splits apart. So it'll be A and then 5 OHs. They're each going to have a -1 charge, which means the A will have a 5+ charge. And we can apply the same thing as we did earlier. So we've got the initial, which will be nothing for the solid in both the equilibrium or the initial case. That'll be 0 initially. And then, this is important, it could become Z and 5Z over here. Any questions so far about this? Anybody? Can, yeah.
No.
Okay. Now the KSP value we're given here is 8.42 times 10 to the -21. The KSP itself will be A5 plus OH minus to the 5th. And then we'll do the 8.42 times 10 to the -21 equals Z, and then 5Z to the 5th over here. I forgot my calculator. I'm going to go get it. I'll be back in a second. Sorry about that. So we've got 5 to the 5th. So that's so that needs to be put to the 5th power as well. Now on your calculator, you might have a caret button. That might be the best way to do that, which comes out to be 3125. So it'd be 8.42 times 10 to the -21 equals 3125. And this is important. It goes Z to the 6th. And that's because it's z times z to the fifth. I'll stop there for a second. Is everybody okay with that? The z to the sixth, how I'm getting that?
You're adding the z to the fifth and the z to the 1, correct?
That's right. That's correct, Miriam. So the z to the sixth then is going to equal 8.42 times 10 to the negative 21 over 3125. And if we want z, we have to take the sixth root of that. So 8.42 times 10 to the negative 21 divided by 3125. And then take the sixth root of that, and that'll be to the power of 1/6. And I get 1.17 times 10 to the negative 4, the z. Anybody have any questions? Seems about right. Let's see, negative 21, sorry. Anybody got any questions so far? Now that's not the final answer, because you can see that if we look at we're looking for POH, which is the negative log of the OH minus concentration. But we see that the OH minus is 5Z, so the concentration of OH minus here is going to be 5, and that's the part that people forget, I think. 5 times 1.17 times 10 to the negative 4. And I get 5.89 times 10 to the negative 4. And if I want the POH, it's going to be the negative log of that. So I take the log of that and then take the minus of it. And I get 3.22 as my answer there. It should be 3.229. I was taking the right sig figs, and you can see there 3.23 would be your correct answer there. Anybody got any questions about that one? Okay. Let's take a look at the practice test and the questions related to this in the practice test. Okay, so the first few questions are about showing how something breaks up in solution. I've often found that people have trouble with this, which is why I put these questions in here so that people can practice them and begin to see the pattern. So for something like this, SbOH5, note that you are given the formulas for certain relevant polyatomic ions. You can see them down here. That way you don't have to go looking them up, or you don't have to memorize them because they are here. And if you've got SbOH5, what I'd recommend you do is draw a picture of what that would look like. And if you see that as being -5, then you know that the antimony would have to be 5+, and the answer you'd put down would be Sb5+, plus 5 OH minus. That would be the answer you put down there. Any questions? Okay, let's look at this one. If you have a Cr3PO42, it would look like that. Note that you have to get the charge of the chromium off the polyatomic ions. You can't just look at it and figure it out, not generally. But the way that works is you've got -6 total on that side, +6 to match the -6, and then each of these would have to be 2+. So the final answer here would be 3Cr2 plus 2PO4, 2PO4 3 minus is what you would write down. It's all type in the box. Any questions? Okay. Nobody has any questions about this? You're all fine with that, huh? All hunky-dory. All right. Now, I like this one here, SNS2. I guess the other thing that's important is that if you had, well, I'll give you an example in a second that's related to this. Whoops. I'm doing that. Hang on. There we go. If you've got SNS2, as a picture, it looks like this, SN and 2 S's. The S's have a 2 negative charge, which makes the SN4 plus. Now you might be wondering, well, how would you know that SN has a -2 charge? Well, you'd have to look at the periodic table, which I think I have got one in here. There it is. And sulfur is in group 6, which is here, which means that the charge on everything in that's going to be -2. So you'd have to know that. But I see that as more intro to chem than anything else. So the answer there would be SN4 plus 2S2 minus. That's where that comes from. Something a little bit different. Let's say it was CrCO3. I'd want you to know that you'd split that up, and that would be the picture. I think sometimes people look at polyatomic ions like CO3 and think that there's 3 of them, and that's how it would split up. But a polyatomic ion, you know how many there are if there's parentheses or not. You can see an example of that over here. There's 5 PO4s, but we know that there's 5 because there's parentheses there and a 5 on the outside. There's no parentheses here, so we know it's just one of these CO3 groups. So that's the difference between something like this and something like this one here. The SNS2, there's actually 2 sulfurs there, and here there's only 1 CO3 group. Does anybody have any questions?
So far we've done...
Sorry, Miriam. Let me turn up the volume here. Yeah.
Sorry, it's me.
Oh,
so
Rebecca,
far
sorry.
we've done individual elements with a polyatomic ion.
Mm-hmm.
Is that how it's going to be, or is it going, or could it possibly have 2 polyatomic ions together?
No, it'll only be one cation and then one either polyatomic ion or one element off the periodic table.
Okay.
But never
Okay.
a combination of the 2.
Okay.
Okay. I think it's just important to know, and you can see I've got them differentiated here, and you can see NiCl3, that's 3 Cl minuses. And then if you had something like this, then you have to be aware that is only one polyatomic ion.
Okay. All right. Thank you.
All right, any other questions? In that case, I'll move on to this last one here. All right, so a slightly soluble salt has the formula A3B2, and I give the KSP value. Now I'm here asking for PB. So let's go through and see what that looks like. And I'll answer any questions anybody has about this as well. Now, you don't really have to necessarily know the charges on any of these things. You do have to know the numbers of ions that you're getting though. So if you've got A3B2, we know that it was splitting into 3 A's and then 2 B's. Now, I could put charges on. I'd say that 3 minus and 2 plus would be reasonable. But you don't have to know the charges here. You just have to know how many we're getting. And that's pretty clear from looking at the formula of the salt. Anybody got any questions so far? Initially, we're going to have nothing there, and then 0 and 0 on the ions, and then 3Z and 2Z over here on the equilibrium concentrations of those. Any questions so far? The KSP is going to equal A 2 plus cubed B 3 minus squared. And then we can plug in that KSP value that we're given, see 6.5 times 10 to the negative 10. And that's going to be 3Z cubed and then 2Z squared. Now that's going to be 108. And then we get that from the 3 cubed, which is 27, and the 2 squared, which is 4. 27 times 4 is 108, and that would be Z to the 5th. So the Z value then is going to equal the 5th root of 6.5 times 10 to the negative 10 divided by 108. So what I'd like to make sure that you can at least get that in your calculator, that you're understanding how to plug that in. And if you have any questions about how to do that, now might be a good time to ask them.
I have an older calculator that I don't think has the button you're talking about to do the root to the 5th.
Has it got a Y to the
Would
X
it be
button?
feasible to find a decimal for 1 divided by 5 and then use that as the power?
You could do that, but have you got a Y to the X? Y to the X button?
Yes.
Yeah, so that's how you would do it. You would do, in your calculator, you put 6.5 times 10 to the negative 10 divided by 108, and then get an equals on that, get an amount, and then do Y to the X, and then you could use parentheses 1/5, or you can just do 0.2.
Okay.
And that will give you the Z value.
Okay.
I get 5.7 times 10 to the negative 3 for Z. Now you got to remember that B, the concentration of B, is equal to 2Z. That's a step that most people forget, I think, which is going to be 2 times 5.7 times 10 to the negative 3. We get 0.0114 or 0.011. And then we can get PB, which is the negative log of that. Negative log of B. And I get so at 1.94 for that. And that's how you come up with the answer. But the most common step that people forget is that one at the end where you have to multiply it by 2 because it's 2Z for the concentration of B at equilibrium.
So alternatively, if we were solving for A, it would be 3.
That's right, it'd be 3Z. If you're looking for
Thank you.
PA, Nathan, yes, PA. The reason I asked for a negative log is because often these result in very small numbers, and these answer boxes, they can handle exponents, but you have to be very careful about the way that they're formatted to get the right answer. So I just prefer to take the negative log of it in order to get an answer that is easier to write into the box. That's why that approach is taken. It's not to make life more difficult. It's actually to make it a bit easier to put the answer in. But you have to understand that wrinkle and what it means to PB. Does anybody have any questions about number 26?
And you used 1.94 because there were 3 decimal places in the answer, so then you did 3 significant figures? Is that how you?
No, actually there's 2 significant figures in the answer, which means we need 2 decimal places on the log.
Got it. Okay, I had that backwards. Thank you.
And will all of our answers be in decimals like they have been in the homework or in the quizzes, or will we be putting the times 10 to the -5 or whatever?
No, most likely they'll be numbers that you can deal with. You know, they won't have exponents on them, generally speaking.
Okay, thanks.
I try and arrange it like that, Rex. All right, any other questions? Okay. Well, let's move on to the next one then, and I'll show you what that looks like. No, I haven't got that here. So on the paper test, question 7 looks like this. And what we're looking for is if precipitation will occur when we have a certain amount of ions from each part of the precipitate joined together. And we do something like this in the lab. I'm hoping that, you know, you've seen this in the lab. I don't know. I suppose it's today actually is when that lab starts. But this is the skinny of it. Let's say we've got this, I'll just call this XY solid as our precipitate. And in one solution, you might have this. This salt. And in another solution, you might have this salt. And then you pour them each into the same container, and we end up getting this solid XY on the bottom. Possibly. Now, this will happen if we have a certain condition met. So let's say we've got XY solid, and it splits into, we'll say, X plus and Y minus. And we have our KSP, which is going to be X and Y together, X plus and Y minus together, like that. So that'll be our KSP value. But we're also associating with that a QSP value, which is what we're going to be looking at before equilibrium occurs. And it's that value. So the QSP is greater than the KSP, then precipitation will occur. if QSP is less than KSP, precipitation won't occur. And you'll notice in a question like this, you are given the KSP value. You can see it here in the actual question. So the issue then becomes, well, how do we figure out if there's going to be precipitation or not? Well, we have to know what the concentrations of X plus and Y minus are in solution. And what I want you to see is that if these are low concentrations, it won't be sufficient in order to make precipitation occur. So it's only if the multiple of these, or the product of these ions, we're multiplying them together, gives a value that's greater than the KSP given. That's when precipitation occurs. So if this is really low and this is really low, you won't see precipitation. If this is high or this is high, you will see precipitation. But the point is, you need a high enough concentration of these ions to get this solid to form on the bottom of the beaker, and that's what we're trying to determine here. Any questions so far? So what's that mean for us? Now, if you look at the A and the B here, the A and the B are what we call counter ions, and they're spectators. They're going to be there in the original solutions. They're also going to be there at the end, but they're not going to form anything. So we're not really interested in their concentration. We do not need to know the concentrations of A or B. Now, the concentration of X in that final solution depends on two things. It depends on X initial, which is in here, and then we have to figure out the dilution. Dilution concentration. See, the thing is that if you've got this solution of X2A and BY3 and you add them together, you end up with a volume that's greater than what either of those two had at the beginning, which means that they both get diluted as well. But we need to, first of all, figure out the concentration of X in the initial solution. And you can see that's going to be entirely dependent on what X looks like in that initial compound. So if it's X2A, you can see that that would mean that there are 2 molecules of X for every 1 mole of A. That's going to affect the concentration of X in the initial solution. And then it gets diluted. So we have to do both of those things in this kind of problem. Does anybody have any questions so far? Okay. Let's take a look at the problems on the test here and what those look like. The first one is what we were just talking about as far as determining whether or not we were going to get precipitation. And it's just related to what I was talking about here. I think you can interpret that from here. But what I want to focus on here was 28, which goes through the whole mechanics of being able to determine whether or not precipitation occurs. So what I'll do, don't want to delete all of this. Just want to delete some of it so we can, well, I might have to delete all of it. Yeah, I'll delete all of it. I'll do a couple of new diagrams for this one. So what we've got here is this solution of AB2 being added to a solution of C3D2. Okay, so let's picture this, see what we're doing here. So we have AB2 in here. We have a certain volume of it. It looks like 170.00 mils. And on the other one, we've got, what is that, C3D2. And that's 300.00 mils. Okay. And we've got a we're looking for the PQSP for A3D2. Now, I'm not giving you a KSP so you can figure out if precipitation is occurring or not. All we're trying to do here is look for the QSP, but then take the negative log of it to get the PQSP. And that's A3D2. Which we know would split into 3 A's and 2 D's. Again, we could put charges on if we wanted to, and I could say 2 plus and 3 minus. That would probably work out, but we're only interested really in A and D. We're only interested in A and D here. We're not interested in B and C. So we're going to first of all focus on the A concentration. And as I said, there's 2 things we have to look at for the A concentration. We have to look at the concentration in the initial solution, and then we have to look at what it would be once it got diluted. Because once you add these 2 together, which I'll do over here, we're going to end up with a certain concentration of A, we'll say A2 plus, and a certain concentration of D, 3 minus. But the total volume here will be 470.00 mils. Which means that, you know, we're going to suffer some dilution here as well. So each of these needs to be done in kind of 2 steps. Let's focus first of all on the A. We've got the AB2 solution. Now AB2 will split into A2 plus 2B minus. So if you drew a picture of it, it would look like that, ABB. Again, we're only interested in the A concentration here. So what I would do first is I am given the concentration of the AB2 as 0.00325 molar AB2. And that would be, we get 1 mole of A2 plus out of that for every 1 mole of AB2. It's not always going to be 1-to-1, by the way. It all depends on what you've got, but that would be 0.00325 molar A2 plus. Now, had it been A2B or something, and we'll see an example of that when we're looking at D, then yeah, we will have to multiply it by 2. But for this one, it is just going to be the same. So that's the concentration of A2 plus in the initial solution, but then we need to look at the dilution. And for that, we use the dilution factor, C1V1 equals C2V2, which effectively is saying that the number of moles of A2 plus aren't going to change, but the concentration will. And we're going to have 0.00325 molar times the volume, which is 170.00 mils. But we're looking for the new concentration when it gets diluted to 470.00 mils. For that, I get 1.17 times 10 to the negative 3 molar for C2. And that's A2 plus. Okay, so I want you to see what we did there. There's 2 steps. First of all, we focus on the initial solution and the concentration of A in that solution. And then we have to figure out the concentration of A once it gets diluted. Anybody have any questions? Okay, now we have to focus on the C3D2. We'll do the same thing over here. squeeze it in down here. So C3D2 will split into 3C2 plus and 2D3 minus. But again, don't worry about the charges too much. We're only interested in the numbers out the front here, really. And we can see that let's see what the concentrations are. We need to figure out the concentration of D3 minus in the initial solution. So that's going to be 0.00355 molar C3D2 times 2 moles of D3 minus for every 1 mole of C3D2. And that's because we're getting 2 moles of D3 minus for that. And that would be 0.00710 molar D3 minus. In that initial solution we're talking about up here in this first one. But then we have to look at what happens when that gets diluted. And again, we're using the C1V1 equals C2V2. And that would be 0.00710, which we just got here, times the volume, which is 300.0 mils, 00 mils. And that equals C2 times the total volume, and you can see that the C2 there would be which would be 4.53 times 10 to the negative 3 molar. And that would be D3 minus. So remember, we're only interested in A2 plus and D3 minus here, so that we can investigate the story as to whether or not that QSP ends up being greater or less than the KSP. But in this case, we have to figure out what the QSP is. I'm going to do that over here in the top corner. So the Q then, or the QSP, is going to be A2 plus cubed times D3 minus squared. And then we can plug in those values that we got here for A and D. So it would be, excuse me, sorry, 1.17 times 10 to the negative 3 molar cubed times 4.53 times 10 to the negative 3 molar squared. And that gives us our value of Q. So let's see. So that's that one squared. And I get for that 3.28 times 10 to the, or 3.29 times 10 to the negative 14 as the QSP value. The PQSP would be to take the log of that and to get the negative value. And I get 13.483. So PQSP would be 13.483. And that would be the answer you'd plug in. All right, so there's a lot of moving parts to this problem. A lot you have to do. So you've got to make sure you understand what you're doing. Yeah, sure, you could mechanically write it down and then try and apply it without understanding it, but I think it's better if you understand it. Does anybody have any questions that would help their understanding of this?
So the significant figures, though, would it be a little bit less?
For which one? For the end?
The PQSP. Oh, no, because it's the negative log. Sorry, 3 and 3.
Yeah, again, it's three decimal places because there's 3 significant figures, right?
Okay.
I know, that's a tough one to get used to, isn't it? The
Yes.
log sig figs. It's not too bad, though, once you get used to what you're looking for. I do give a bit of an explanation for that, I think, in one of the videos. I hope I do. I'm not sure if I do. Rebecca, did you want an explanation as to why it's that number of significant figures? I can give you a more math-oriented explanation.
No. I remembered it. It's what you're saying, getting used to it.
Right.
Yeah, no, I did watch it.
Okay.
Trying to keep it all straight.
Okay. Does anybody have any other questions that they want to ask about this? All right. Sorry. Rex?
Nope, no questions.
Okay. Does anybody have any other questions that they want to ask about anything else that's in ungraded copy of practice test 2? Any other questions about anything else in ungraded copy of practice test 2? All right, well, if nobody has any other questions, then I will leave it here for today. If you have any other questions, you can always email me and we can try and get them sorted out. But between all the Zoom sessions I've done, I did 3 for this particular test because it was a little bit more complicated. Then I think that should be sufficient to get you through everything. But if it's not, then let me know. We'll set up a Zoom meeting and see if we can sort the problems out. Okay, anything else? Any other last requests here?
Nope, I think that's good. Thank you.
All right, folks. I'll talk to you all later then. Thanks for coming. Appreciate it.
Thank you again. Bye.
No worries. Bye-bye.